Hello friends, welcome to my channel Civil Structures. Today our topic is to design the eccentric footing. Now when the footing is subjected with uni-axial or the biaxial movement along with the axial forces and they consider as a eccentric footing. Okay, there are basically two types of eccentric footing. One is with uni-axial movement and one is with the biaxial movement. We will design the uni-axial moment eccentric footing when the footing is subjected with only one moment, whether it is mx or it is my. Now for the biaxial moment footing design, when the footing is subjected with both the moments along with the axial forces. In this video, I will show you how to design the biaxial moment eccentric footing. Now let's see one example here. Design a foundation having the rectangular column 300 by 600 mm. The column subjected with the factored axial force Pu 770 kilonewton. Moment about x is 165 kilonewton into meter and the moment about y is 75 kilonewton into meter. All of these moments are also factor moments. The soil bearing capacity is 200 kilonewton per meter square and you can use M25 Fe 415. Now let's see the given data which is given here. Now our first step is to determine the size of footing. So first of all we have to determine the area. How much area we require to determine the dimension of the footing. The formula for the area is the total force on footing upon the soil bearing capacity. Here for the total force on footing is the total unfactored axial load on column plus the 10% of this axial load as a self weight of the footing. Now let's calculate how much amount of factor load do we have? 770 kilonewton. So I'm doing it unfactored. 770 upon 1.5. It is 513.3 kilonewton. Okay. Do the summation which is 513.3 plus we have to do the 10% of this particular axial load. So 10% of the axial load. Okay. And finally the total load is 564.6 kilonewton. Now let's calculate the area. Okay. For area we have to put this value 564.6 divided by soil bearing capacity which is 200. The answer is 2.82 meter square. Okay. So our required area should be 2.82 meter square, right? So let me just write here area required is 2.82 meter square. Okay. Now we have to determine the dimension of the footing. Before fixing the dimension, let me tell you some basic things to choose the dimension. As you can see in the diagram, we have rectangular column, right? And definitely we will provide the rectangular footing, right? So we will choose a dimension of the footing in such a way that it has the same length of projection in both direction. You can see the projection, it means the cantilever portion after the column face, right? So for the longitudinal direction, here is my cantilever projection. So in longitudinal direction, the value is x, I'm assuming here. That should be same for the lateral direction also. Okay, so both these values should be same. In such a way we have to determine the dimension of the footing. Now how to do that? For that, let's take a difference between the dimension of the column. And my dimension of the column is 600 by 300 mm. Okay, I'm taking the difference 600 minus 300, it is 300 mm. Okay, so the best way is to keep the difference between the dimension of footing. It should be 300 mm or we can say it is 0.3 meter, right? The other criteria is, let's see here is a net upward pressure for the biaxial movement footing. Okay, you can see in the diagram, here is a pressure diagram for the biaxial footing. Okay, you can see here is a footing. Here is a column, okay, my moment about x, moment about y. Here is a pressure diagram along longitudinal direction and pressure diagram along the lateral direction. You can also see the values for the P maximum and P minimum for both the pressure diagram. Okay, now you can see the basic condition for the pressure diagrams, that the P maximum should be less than soil bearing capacity and P minimum should be more than 0. It means P minimum should not be less than 0. It should not be negative, right? So whatever value you have calculated for P minimum, it should be some positive for the both direction, right? Now you can see the formulas here, right? Where P is a total axial load and I must say it is unfactored load upon the area of the footing plus the moment about x upon z is in section modulus in x direction and for zy is in section modulus in y direction, right? Whatever pressure diagram you are seeing here in this diagram, which is in 2D manner, but in actual it occurs in 3D at the bottom of the footing, right? So I hope you understand this both criterias. With the help of that, let's choose the foundation dimension. I'm taking first P 2 meter and L is in 2.3 meter. As you know that we have to keep the difference between two dimensions, it should be at least 0.3 meter, right? Now let me write here. See, I have prepared a table where I can determine B, L, area, section modulus for both dimensions, P by A, M by Z for both dimensions, and P maximum and P minimum. So we can easily understand how much dimension should be more preferable. Okay. So for the first, as I told you, I am taking 2 and the length is 2.3. Okay. Now what is the area? It is just L by B. And the area is 4.6 meter square. Right. Okay. And I am talking in terms of meter width and length. Okay. I hope you know longitudinal dimension consider as length and the lateral dimension consider as B. Right. Then ZX. ZX is nothing but the section modulus. So ZX, the section modulus, and formula is BD square by 6. And for section modulus in terms of Y, it is DB square by 6. Okay. If I calculate the value, I can get 1.7 and 1.5. Then let's calculate P by A. So what is P? Unfactored load. I think we calculate here 513.3. So 513.3 divided by area, which is 4.6, which is 111.5. Right. Now mx upon z. Here we have to take moment about x unfactored, right? I think we have to do the unfactored mx 165 upon 1.5, 110 kilonewton into meter, and for my it is 75 upon 1.5, right? The value is 50 kilonewton into meter, right? Okay, good. Now let's do this mx upon zx. So mx upon zx is 62.3, and for my it is 32.6. Now let's calculate P maximum. Okay, so what is P maximum? Okay, so here is a formula for P maximum, and if we add all of three values to 06.5 kilonewton, right? And for P minimum, I just have to take value negative instead of positive one here. Okay, so P by A minus, okay, and it is my upon zx minus. You can see here only we are taking the negative value, right? Okay, for P minimum, if I deduct all of these three values, it is 16.5, right? So now, as you can see, we cannot take this particular dimension. Why? Because this condition is not satisfied here, right? So here P maximum should be less than SVC, and our SVC is 200, right? 200 kilonewton per meter square. But my P maximum here is 206.5, right? So I could not take this particular dimension of my foundation. Now let's go further. So I'm increasing my width by 0.1. Okay. So if it is 2.1, then length will be 2.1 plus 0.3, it is 2.4 meter. Now let's calculate the area. 2.1 multiplied by 2.4, and it is 5.04. The value of zx and zy, the formula is similar. Let me write the values. For P by A, it is 101.8. And how I calculate my P by A, and it is 513.3 divided by the area, it is 101.8, correct? Now for mx upon zx and for my upon zy, let me write the values. Okay, now for the P maximum value, if I'm adding all of these three values, P maximum will be 184.2 and the P minimum will be 18.9. Okay, so I think this dimension will be fit in our condition. As you can see, the P maximum is less than soil bearing capacity, right? And of course the P minimum is more than 0. So now we are taking this particular dimension 2.1 in lateral direction and 2.4 in longitudinal direction. Okay, so after trial and error method, we have finally fixed our dimension of the column. You can see in the longitudinal direction it is 2.4 meter and in the lateral direction it is 2.1 meter. You can also see the cantilever projection values for both the direction, they are same 0.9 meter, right? Now here is a pressure diagram, the lateral direction. It is a lift pressure diagram. The direction should be upward because here is a pressure coming from the soil portion, right? Okay, now also we have to calculate P maximum and P minimum for both the diagrams, right? So I have already calculated the value of P maximum and P minimum here. You can see with this particular formula. We already calculate for this P by A plus M by Z for the X direction. Okay, here we are taking P by A for this particular 101.8 value plus M by Z. Okay, so if we do the total summation of these two values, I can have the value 156.04 and the unit is here kilonewton per meter square, right? And of course this value is less than SDC, right? For the P minimum you can see the formula. I can determine 47.28 unit is kilonewton per meter square, and this value is also more than 0, so our both condition is satisfied. Similarly for P maximum and P minimum along the Y direction, okay, 130.18 kilonewton per meter square, and here it is also kilonewton per meter square, right? Now I hope you can understand the basic dimension and pressure diagram for this particular footing. Okay, so our next step is to determine the bending moment at the face of the column. Why? Because with the help of bending moment we can determine the depth of foundation and we can also determine the reinforcement for the particular foundation. Okay, we all know the formula for bending moment is force into perpendicular distance. Now what is force here? So do not confuse that our pressure diagram values are the forces. No, why? Because whatever values you have determined for the upward pressure, okay, that values units are kilonewton per meter square. So they are nothing but the stress, right? Because and that is P by A, correct? And you have to determine here the forces, and we know that the unit of the force will be kilonewton, correct? So how to determine the force? With the help of these particular values, we just have to determine the area of this section, right? And we can determine the force. Why? Because we have to determine the bending moment at the face of the column. So we have to calculate the area of these trapezoidal section. Now the other thing is, whatever values you are seeing here, that is 156.04, 115.25, the kilonewton per meter square, okay, they are just they are just a coordinate of this particular 2D section, right? And we have to determine the area for our complete pressure diagram 3D. Okay, so here is the complete pressure diagram 3D. What is the beneath the footing, right? So what we have to do? We have to determine the area of these complete section, and whatever you see in the pressure diagram in this drawing, okay, in this diagram, it is just this particular portion, but we have to determine for the complete 3D area. Okay, so let's start with that. Thing is to our basic idea is to determine the area of this particular section, but as you know, the shape of this section is trapezoid. So what I'm doing, I'm just dividing this section in two particular triangles, right? Triangular 1 and triangular 2. Okay, so we just have to determine the area of this two triangle, and you just sum both values, right? Now let's start. For the area of first triangle, 1 by 2 multiplied by 115.25, you can see here vertical coordinate multiplied by horizontal coordinate here, and we know the value of the horizontal coordinate is 0.9 meter. Okay, so just multiply and you have the area of this triangle in 2D, but we have to calculate in 3D. So see here, okay, so we have to multiply this particular distance in either direction, right? Or we can say the width, which is 2.1 meter. Let me just write 2.1 meter. Now let's do for the second triangle. It is 1 by 2 multiplied by 156.04 multiplied by 0.9 multiplied by 2.1. Same, okay. The only change is the values of these two vertical coordinates, right? Now so here is the value for our force, but we have to determine the moment, so we have to multiply with the perpendicular distance. Okay, and if you want to determine the perpendicular distance of the both triangles and they are nothing but the center of gravity. So let's determine the center of gravity for each and every triangle. If we calculate the CG from this direction, and for triangle 1, my CG will be 0.9 divided by 3. So it is nothing but the 1 by 3 multiplied by 0.9. Similarly, for the triangle 2, we have to do like this, 2 by 3 multiplied by 0.9. Okay, you just have to do summation of all of these values and we can have finally our moment. Okay, so here the value of moment is 121.42, and if it is a moment, my unit is kilonewton into meter. Okay, we just have to determine the factor moment, 121.42 multiplied by 182.1 kilonewton into meter, and that is the final factored moment, and that is a final factored moment about x direction, right? Now similarly, we have to calculate the bending moment for y direction, right? So the procedure is similar. You can see here the pressure diagram. The coordinates for the pressure diagram values, you can see the units are in kilonewton per meter square. We have to determine the moment, and that is force into perpendicular distance. Okay, so we have to determine area of this particular portion, right? Why? Because we have to determine the bending moment at the face of the column parallel to the lateral direction, right here. Okay, and our pressure diagram in 3D, you can see something like this. Okay, so we have to determine the area for this particular section. Okay, now similar as the last one, we have to determine similar as mx to determine the area for trapezoidal one. I'm just dividing this area into two different triangles, triangle number 1 and triangle number 2. Okay, let's start with calculating area. 1 by 2, the first ordinate is 105.89 multiplied by 0.9. Same. Why? Because this horizontal distance, or we can say the cantilever projection of footing, is 0.9. Okay, and we have to also multiply the either distance, and for the parallel, for the lateral direction, my either distance is 2.4 meter. Okay, let's see this here. Okay, here this distance is 2.4 meter. We just have to multiply here. Area for the second triangle is 1 by 2. The ordinate is 130.18 multiplied by 0.9. Again, we have to multiply 2.4. Okay, and here is the area of these two different triangles. Now we just have to multiply the perpendicular distance to determine the moment. And as we know, the perpendicular distance for the triangle is nothing but the CG. Okay, so if we determine the CG from this distance, and it is 0.9 by 3, and for the second triangle it will be 2 by 3 multiplied by 0.9. You just have to do the summation of these values and you can have the value of my. My is 118.63 kilonewton into meter. Just have to do the factored MUY, and that is 118.63 multiplied by 1.5, and the final value is 178 kilonewton into meter. And so we have finished with our calculation of bending moment at the face of the column. Next step is to calculate the depth of footing. Okay, as we have already calculated our bending moment values for both directions. With the help of that bending moment value, we have to calculate for both direction, right? Now I'm assuming here for the balance section. So let's write the formula for the balance section. Here is MUX is equal to 0.138 FCK BD square. MU we have determined here. Okay, let's see the value. MUX is 182.1 into 10 raised to 6, and the unit is Newton into mm. Okay, 0.138 FCK is 25. Here the width is in B. So width for the x direction, whatever value we have multiplied with in terms of width is 2.1 here. Okay, so if I write 2100, it means 2.1 meter and D square. So here D we have to determine, and I can determine the value of dx is 158.53 mm. Same as for dy. Okay, use to determine the value of dy. We can use here moment about y is MUY 0.138 FCK BD square. Okay, The value of MUY is 178 into 10 raised to 6 is equal to 0.138. FCK is 25. Here my B is 2400 into D square, where D we have to determine here, right? And I can calculate my value of dy is 146.6 mm. But we have to take our depth of the footing in such a way that our footing should not fail in one-way shear and two-way shear both, and that's why we have to keep our depth almost 2 to 3 times higher than whatever we calculated. Okay, so what I'm doing here, I directly assume first my capital D is 500 mm. Okay, and if I'm taking the clear cover 50 mm, then effective depth of X is 500 minus clear cover minus assumed bar diameter divided by 2. So I'm assuming here the bar diameter is 12 mm we are taking, and the value of D of X I'm taking is 444 mm, correct? And for dy, capital D minus clear cover minus a complete bar diameter minus the bar diameter divided by 2. Why? Because my reinforcement, because here my reinforcement in both of the direction, right, and the reinforcement for the y direction, they are over the x direction, and that's why we have to deduct the complete bar diameter. Okay, and the value here is 432 mm, correct? So whatever effective depth we are taking here, D of X is 444 mm and dy is 432 mm. Okay, and of course we will require here the average depth. So let me just calculate my average depth, and that is 438 mm. The remaining calculation for the reinforcement along both direction, one-way shear check and two-way shear check, also with the detailing drawing, we will see in the next part.